Let's integrate a number of indefinite integrals using a technique called U substitution. So there are three examples here. There's A, B, and C. All of them are indefinite integrals. So what we're trying to do here is find an antiderivative, in which I should say that we're trying to find a family of antiderivatives. So for indefinite integrals, make sure you put a plus a constant to indicate that family after you integrate. Okay? So why don't we substitute for example A? So why don't we let U equal x minus 1. Use the language of differentials. So here's a differential, is du, and the other differential here is the derivative of x minus 1, and then times the differential dx. The derivative of x minus 1 is 1, and then times the differential dx, so we got du is now equal to dx. Now, we have a substitution for x as well, so why don't we find out what x is? X here has got to be u plus 1. And now we're ready. We're ready to substitute everything. So this integral here is now in terms of u. So we substitute x, so we have u plus 1, and then the square root of u, and then dx is du. Voila! Isn't that beautiful? So now we have what? U to the 3/2 power plus u to the 1/2 power, and we need to integrate this. So remember, for the power rule here, we add 1 to the exponent, and then we will divide by the exponent. So this is 2/5 u to the what? 5/2, and then we have plus 2/3 u to the 3/2. Let's make that a 3. Good. And then, of course, put this has to be a family of antiderivatives, so plus a big constant c. Oh, usually, if the problem is given in terms of x, we want to finish in terms of x. So why don't we write this as 2/5, and we would put this back in radical form. Raised to the 5th power, and then plus 2/3 square root of what? X minus 1 raised to the 3rd power, plus a constant. So there we go. So that's how we do A. Why don't we try to do B as well? Let's move B over here. This time we'll let U equal what? What do you think? Why don't we try the natural log of x? So our differentials, du, and we need the derivative ln of x. So that would just be 1 over x for x greater than 0, and then times the differential dx. Now we're ready to substitute. This is gorgeous. So why don't we say this is now sine of what? U du. And of course you know how to integrate that. Negative cosine of u plus a constant. But what's u? Simply ln of x plus an arbitrary constant. So there you have your family of antiderivatives. Nice. One last example here. I'm going to clear the board. Let's clear the board. Bye-bye. I missed this. Let's clear this too. Oh, what happened? Let's clear this as well. And let's move this over here. And why don't we integrate this indefinite integral? This, of course, requires a little bit of magic. And remember, magic just means algebra. So, why don't we factor? Let's factor out an a squared from the denominator. So we have 1 plus what? How about x over a quantity squared? Why don't we use a bracket here? That makes it a little bit neater. There we go. Times the differential dx. Ah, gorgeous. We're ready. We're ready for our u sub. Let's let u equal x over a. Let's find our differentials. Differential du is now equal to 1 over a. The derivative of x over a is just 1 over a times the differential dx, because we want the language of differentials. That would be nice. And if we could do a better substitution. Why don't we try this? Notice a is non-zero, so we're not dividing by 0 here. 1 over a du is equal to 1 over a squared dx. I think that would be a better substitution. Now we're ready to substitute. 1 over a squared dx is 1 over a du. So let's leave 1 over a here. We have 1 over what? 1 plus u squared du. Isn't that gorgeous? Well, shoot. That's a familiar integral. That is simply 1 over a inverse tangent of what? U. But what's u? 1 over a inverse tangent of x over a. And of course, we want a family of antiderivatives because this is an indefinite integral. So make sure you put a plus c there at the end. And voila. Did that say that? You know what? This needs to say integrate. There we go.